In the last video, we looked at the absolute value of a complex number, with the absolute value being what we would consider a distance measurement in a real plane. But remember, this is the complex plane, so these words distances and angles, they don't really mean the same thing, so they're not given the same names. So the absolute value of this complex number is the measurement of from the origin to this point. If this was a real plane, what would that distance be? And we know how to calculate that because we've had some practice with that now. So if we said that this absolute value, we'll call the absolute value z, the complex number z. So if the complex number is 2 plus 3i, then the absolute value of the complex number, or the modulus, so we still use the absolute value bars, is equal to the square root of 2 squared plus 3 squared. And so that becomes the square root of 13. So the absolute value of this complex number is the square root of 13. Now we also need to know where is the complex number, because the absolute value of 13 could be anywhere. It could be over here at minus 2 plus 3i. It could be down here. That absolute value, it would make a circle. Any place that is root 13 away from the origin has an absolute value of square root of 13. And so we need to also know the angle where it's sitting. And in the complex plane, which again is not x and y, it's not really a measurement with a protractor because we're not in real space where we can put a protractor down there, right? But if I was to just sort of draw in my absolute value distance there, that this is the square root of 13, I create what we're very comfortable with by now, this right triangle, right? Where the real part is 2 and the imaginary part is 3, and I can get this angle. In the complex number system, that angle is called the argument, because since we're not in real space with an x and a y axis, it's not truly an angle you can measure. So in the complex number system, we call this theta to be the argument. But we get it the same way. We would say tangent of theta, we calculate it by doing opposite over adjacent, 3 over 2. And when we do that, we get that the angle is equal to 56.3 degrees. Or if you want, you can do it in radians, is 0.98 radians. Okay, now what does that do for us? What this allows us to do is to write our complex number, our 2 plus 3i. We can write that in a trig form. And the trig form is going to be the square root of 13, right, times the cosine of our angle times the cosine of 56.3 plus the square root of 13 times the sine of 56.3 times I. And we have to put our degrees on so we know we're in degrees. That is the trig form, or the polar form, of a complex number. Now think about it. If I look at this little right triangle and I think about the trigonometry that goes with it, well, if I said the cosine of this argument, the cosine of the argument is equal to 2 over root 13. So 2 is equal to root 13 times the cosine of theta. So root 13 times the cosine of theta is my real part of my number. And we could do the same for the 3, that the square root of 13 times the sine of the angle, the square root of 13 times the sine of the angle, is going to equal our opposite side, is going to equal 3. So this expression is equal to our imaginary part. Now we like to clean up our complex number in trig form by putting the modulus, or the absolute value, out front, and then putting in parentheses cosine of the angle plus, and we put the I in front of the sign so it doesn't get lost, I sine of the angle. And that's the trig form. This is the same as our rectangular form. These two are equivalent, right? Now let's just prove to ourselves that they're equivalent. We're just going to do the multiplication back in, just like we did up here. Just going to say, if you were given a number that looked like that, you could get the rectangular form anytime, because all you'd have to do is distribute your absolute value in. So we would say the square root of 13 times the cosine of 56.3, and we would get, I'd put the whole thing under the square root, so that was a mistake on my calculator. Not watching this one. Square root of 13, and then I have to come out of the square root, times the cosine of 56.3, and we get 2. So when I distribute that square root of 13 in, the square root of 13 times the cosine of 56.3, I get 2. That's the real part. And when we do the square root of 13 times the sine of 56.3, we get 2.9993. So the square root of 13 distributed into the sine of 56.3 is equal to 3. And so this number is just a different way. It's the trig way of writing the rectangular form of a complex number. Now, why would we want to write it so complicated? Because multiplying, dividing, and raising to powers are way easier. Much, much, much easier if you're in the trig form. Okay, so let's do one more. Minus 4 plus 5i, so I've put that up here. And let's write this in the trig form. We have to get its argument, we have to get its absolute value, and we'll call this complex number number 2 because we're using, a lot of times complex numbers are given as z's, just the letter z, a lot of times. Okay, not always. All right, so we're going to say that the absolute value of z2 is equal to the square root of 4 squared plus 5 squared. And so the absolute value, which you know the other name is the modulus, is going to equal the square root of 41. Okay, and then what is the angle? So I'm just going to picture my absolute value going there, and I want this angle. Okay, so we've always talked about, well, let's just draw the right triangle and do the thinking that goes involved. So we're going to put our right triangle in to the real axis. And we have 4 on the real axis in the negative direction, and we have 5 in the vertical direction. And so this little theta in there, tangent of that theta, is going to equal 5 over 4. If we drop the negatives, we get the acute angle that is inside of the triangle. So I'm going to do it that way first, and then I'm going to show you the general way that you can decide which way you prefer. So tan inverse of 5 divided by 4, this is equal to 51.3 degrees, or it's equal to negative 0, it's equal to positive 0.89 radians. Okay, so we can do our angle in either, and on this way we'll do them in both. Now, that is not the angle from the origin, right? So we know that if I was to go to measure from here to this point, well, that would be the same as measuring 180 or pi radians and then subtracting that theta, going back that amount. And so our argument is going to equal 180 minus 51.3 degrees, or pi minus 0.89 radians. And so when I do those, I get 120, this one becomes 128.7 degrees, and this one becomes pi 2.24 radians. And so now we can rewrite our rectangular form. We can say that negative 4 plus 5i is equal to the square root of 41 times the cosine of 128.7 degrees plus I sine 128.7 degrees. We could also say that it's root 41 times the cosine of 2.24 radians plus I sine 2.24 radians. Okay, so those are both the same as the rectangular form of this. And remember, if I'm just given the trig form, all we have to do to get the rectangular form is just multiply the modulus back in, the absolute value back in. So the square root of 41 times the cosine of 128.7, and we get -4, which was our rectangular real part. And then if we do the square root of 41 times the sine of 128.7 degrees. I'm in degrees, so if I put my calculator in radians, mode radians, I could use the radian version, and I get 5, right? Which is exactly what I had. Now, there is another way to calculate the argument, the theta. When you have negatives, if up here I had left the -4 in, so let's just see what happens if I leave that -4 in. And we talked about this when we were in trig as well, so this shouldn't be new, but if I had said tangent of theta is equal to 5 over -4, and so theta is equal to the tan inverse of 5 over -4, well, remember, tan inverse is only defined in quadrants 1 and 4, right? Tan inverse was only from -90 degrees to 90 degrees, or -pi/2 to pi/2. So if I do tan inverse of 5 divided by -4, I get -51.3. It doesn't see the angle being in what we would call the second quadrant. It doesn't see it up here. Tan inverse can only give me answers that are in the quadrant 1 and quadrant 2 that we would typically talk about, right? So if I'm thinking about the real axes, the Cartesian coordinate system, x's and y's, my tan inverse is going to give me this number, right? So this is -51.23, -51.3 degrees. Just like this theta was 51.3 degrees. Because look at their vertical angles, so they have to be equal. So how would I get my desired angle if I know that this is -51.3? Well, look at, I'm going 180 around. This is a line. It makes part of a vertical angle. And so what I would say is I would do -51.3, but then I want to be in the opposite quadrant, so I would have added 180 degrees, which really is the same as the thought process we went through when we said, oh, this little acute angle, if I subtract that from 180 degrees, I get the desired argument of my problem. And so it's the same math. I like to draw right triangles and then decide what my angle is by looking at the diagram and the location I'm in. But you are certainly able to just put the negative into the tangent function. And if you're not in quadrant 1, then you would have to add 180 to your answer. So if you're not in quadrant 1, you would add 180 to your answer. If you're in quadrant 4, it's going to come out to be a negative, right? And so if you didn't want your angle to be a negative argument, you could add 2 pi to that and come around the positive direction. Okay, and that's all a review of our trig, that we learned how to do these coterminal angles and how to find the angles. It's just in complex numbers we call them the argument.